Hey everyone, this is the last main teaching video. There are also proof practice videos. This is the last video. I'm introducing new stuff, new material. I'm combining 8.2, 8.3. Those are the two sections on equivalence rules. So in this video, we're going to learn the 10 equivalence rules that we'll be using. We'll talk about how equivalence rules differ from implication rules, how to use them. They have a couple different qualifications, and we'll talk about new tips that these equivalence rules open up for strategies for constructing your own proofs. All right, let's jump into it. The first of our equivalence rules is going to be double negation. This one is pretty straightforward. It's easy to think about. If you have a statement, you can replace it with two negations out front and then that statement. But here is where we'll see for all of our equivalence rules something that's different from all of our implication rules. For implication rules, they're one directional, right? So modus ponens, right? If you have P then S and you have P, well, then you can conclude S, right? Well, and that's just one directional. But equivalence rules, and this is true for all of the equivalence rules, they're two directional. So yes, if you have P, you can replace it with this. But if you have not P, you can replace that going the other way with just P. So there are two ways. There's no beginning and end. You can start on one side and go to the other side. In fact, we'll just use these four dots like this, kind of like an equal sign, but it's just dotted that to just mean equivalent. So this is equivalent to that. So here's some examples. Line 3, we use double negation on line 1. We replace Q with not Q. Line 4 also comes from line 1. Here we actually didn't just replace Q with not Q. We replaced the entire line 1 with double negation of the entire line. So notice the difference between 3 and 4, right? This is a double negation of just Q, but this is a double negation of that whole statement. So either way you do it, these are both instances of double negation. Line 5 comes from line 2 here. Here, instead of going from the left to the right, we went from the right to the left. Take 2, we basically drop these two negations to get line 5. So that's going from right to left. Then in 6, we took 2, and what did we do? Well, we left everything the same except the L or G part. For that, we replaced L or G. So P is standing for L or G, and we replaced it with not L or G. So this gets us to another important difference from our implication rules. We already saw they're two directional for equivalence rules. Another difference is equivalence rules can apply to just part of a line. So in this example, we added two negations right in the middle there. The entire line 2 wasn't being replaced. Instead, we just replaced part of it. And the reason we can do that with equivalence rules is equivalence rules are just about two things that are equivalent. So if they're equivalent, you can replace one with the other, and they're equal. And so implication rules are different because they're going from some statements, right, to something else. They're not saying that this is equivalent to anything. But since this is just an equivalence, right, you can go either way. Next up, we have commutation. We can just abbreviate it like this. And this, we're just switching what side the statements come on either side of a disjunction or a conjunction. So there's two versions of this. There's a version for disjunction and a version for conjunction. The idea being, for both of these types of statements, the order that each side comes in doesn't matter, right? So you can say, right, pigeons or seagulls. You could say seagulls or pigeons. There's no significant difference, logically speaking, between those two types of statements, right? But the same thing holds with and, right? So you can just switch the what thing comes on the left or right. So let's see, here's an example, right? This is the straightforward one. We just switch which side by our commutation rule. And how do you remember this rule? Well, commutation, think of like commute. So I remember the name of this one because the P commutes, like you commute to work or commute to school. The P commutes to the right and the S commutes to the left. So commute means they're commuting to the other side. This example right here, we could do commutation to switch. The T is being replaced. So the T is representing where P is here. And then this whole statement, L or G, that's standing for the S, right? So we could do that and switch this and this. That's what we did in line 2. But because this is an equivalence rule, we can apply the rule to just part of the line. So that's what we did in line 3. We just applied commutation to inside the parentheses and ignored this. So in line 3, we just switched the L and the G part. So we got G or L instead of that. So you can do that, and remember that you can do that with equivalence rules. We also have association. AS, here we're changing which statements are associated with each other, you might say. Which ones are associates? So we also have two versions of this one. It works for disjunctions and also for conjunctions. So here we have a disjunction where one side is itself a disjunction. And we can just change which two things are associated, right? So P or S or R, right? It doesn't matter that much where the parentheses are. This is going to be equivalent to that. But we still, of course, need the parentheses in there to follow our rules. But for these statements, we can just, instead of S or R being associated, we can switch that to P or S being associated, right? And of course, we can go either way. It doesn't matter which side, right? These two associated things are on the left side. Here, it's on the right side. So we can go either way. And it also works for conjunction, and, right? But you don't want to mix and match, right? If you have an and, you can't have an or here and have it still work. So for example here, this is an example of association. Notice that here, instead of an atomic statement, we have not L. And of course that's fine, because each of our lowercase letters in our rules can stand for any statement, whether that's an atomic statement or something more complex, like here, not L. So this works. What about this? No, you can't do association with this. It's got this negation out here. The negation here is fine because not L is what's replacing S in the rule, right? Everywhere S occurs in the rule, you have not L. That's fine. But here, that's not going to work because you can't replace something. You replace what? S with E. what do you do with the not out here? It's not going to work. The test is, can you replace each letter in the rule with some statement and then do it uniformly on both sides? If you can, then that's a correct application. If you can't, then it's not. What about this? So does this work? No, it does not work, because you got a mix. You got and here and you got or there. So just changing this instead to be like G and T or X, that's not going to work. Here's why this doesn't work, association, when you have a mix. Let's take that and see if we try to do association to that. So let's say, for example, that G is false, T is false, and X is true. Is this whole statement going to be true or false? Well, if you have false and false, this conjunction is going to be false, and the whole disjunction, because it's got one side true, right? It's got false, true. This whole side is going to be true. So this statement comes out true when G is false, T is false, and X is true. What about over here? We have the same assignment, false, false, true. Is this going to be true or false? This is actually going to be false. We can see that already, because a conjunction needs both sides to be true in order for it to be true. It's got one side false already, so we know that this whole statement right here is false. So when this statement is true in this example, this statement over here comes out false when all the atomic statements have the same truth value. So you can't replace this statement with that statement without changing something about what you're saying, right? When you say this, it could be true, but when you say this, assuming everything stands for the same thing, it could come out false. So they're not equivalent. You can't replace one with the other. That differs from everything that is a correct use of an equivalence rule, because when it does follow the equivalence rule, you're always going to come out with the same truth value on either side of the equivalence. Next up, we have DeMorgan's laws. So this one is maybe a little less intuitive, but it's super useful, and you'll get the hang of it. Here we have two versions. If you have the negation of a conjunction, that's equivalent to saying a disjunction with a negation on each side. So this says, if we read it, not both P and S, right? So this is both P and S, and the negation of it is not both P and S. Well, this is just saying either not P or not S. So here's an example to help make sense of that. Let's see. So Spuddy is not both a dog and a cat, right? Spuddy is not both a dog and a cat. Therefore, so either Spuddy is not a dog or Spuddy's not a cat, right? That makes sense, right? If he's not both a dog and a cat, he's either not one or not the other, right? So that makes sense. And of course, you can go either way. What about the other version? The other version goes from the negation of an either or, and it gets a conjunction of two negations. So let's see. For example, it's not true. Let's see. It's not true that either hydrogen or oxygen is a metal. All right. It's not true that either hydrogen or oxygen is a metal. Therefore, hydrogen is not a metal and oxygen is not a metal. All right. So you can go from that denial of a disjunction, right? Not either, therefore not this and not that, right? And of course you can go the other way as well. Let's look at some examples. So this line right here, if you have it as a premise and you try to apply DeMorgan's to it, what could that look like? Well, it looks like our candidate for, so if we apply DeMorgan's, let's apply it to the left side of our conditional. This whole statement's a conditional. Let's apply it to the antecedent. So we have the denial of a conjunction. So that is like the left side of the first version of DeMorgan's, and we're going to replace it with the right side. So everywhere, so what's P stand for? P stands for B and S stands for H. So when we replace this part of line 1 with something else, we're going to write what? We're going to write not B or not H. That's what's going to replace this part of line 1. Now, we're going to have to write the rest of line 1, but notice what we did. We basically like distributed the not sign to each part of the stuff in parentheses, and then we flipped the sign. So we flipped the and to an or. Notice on both versions it flips. So here we apply the negation to both, right? And we flip it to an or, from an and to an or. Here we go from an or and we distribute that negation to each side and then flip it to an and, right? Same way when we're going right to left. We pull the negation out and put it parentheses, and then we flip the and to an or. So that's the idea. You got to move the negation either in or out, and then you got to flip the sign. So that's just this part, but what's the rest? Well, it's going to be the not L. But of course, now we're going to need parentheses, right? In our rule, we don't have parentheses, but we're going to have to add them here because this is just part of a longer statement. So we got to make sure that ambiguity doesn't come in. So this is the full correct application of DeMorgan's to line 1, right? You can't just write that first part in. What about this example? So here, let's apply DeMorgan's to this part of line 1, right? The right side of the biconditional. I've already written the left side. We're not doing anything to that, but let's apply DeMorgan's to this. What is it going to look like? Well, this is similar to the right side of version 2. And so what we're going to do is pull the negations out like this and flip it to an or. So it's going to look like not T or S instead of what we had in line 1. And our fifth new rule, equivalence rule from 8.2, this is contraposition, or we can just abbreviate it like this, contraposition. So this is going to work with conditionals, if then. So if we have a conditional, what we can do is switch the sides that each thing appears on and add negations to each. Of course, we can go the other way, switch the sides and drop negations from each side. Why does that work? Well, let's say P stands for it's raining, and S stands for there's precipitation. So if it's raining, then there's precipitation. Well, then this would be if there's not any precipitation, then it's not raining, right? And those two statements are equivalent. So this example, is this an example of contraposition? Yes. So here, what's standing for what? Well, P is being replaced by this whole stuff in parentheses, and the S is being replaced by L. So we switch the sides, right? The whole thing, B and H, is what is being replaced for P, and then we add a negation. What about this? Yes, this also is a correct use of contraposition. Here we just applied contraposition to this side of the disjunction. So we have an either or, and we just ignored the left side and applied contraposition to the right side. And we're actually going from right to left. So we started with, within this parentheses, a conditional, and both sides are negated. So we switched the sides and dropped a negation from each. Now notice, of course, this has two negations. So when you drop a negation, it's now just going to have one. So see what we replaced with what? In our starting line, this is like the right side of the rule. So S and S, right, there's no replacing going on, but P, that's actually being replaced by not C, right? Everything inside the green circle. So when we apply that, now we get the left side, and everywhere P occurs, it's replaced by the same thing, right? P was replaced by not C there and not C in the result. So it's replaced by the same thing every time. So that's correct. And just like in the rule, we have a not in front of each. That's what we have here. And then we drop that here and switch the sides. So hopefully that helps you see how this is a correct application of contraposition there. With our new equivalence rules, let's try to use them in some proofs. Now, of course, you can still use all of your implication rules, and you'll need to use them probably pretty much all the time. But now we have some more tools in our tool belt. We can use our 5 new equivalence rules from section 8.2. So let's try this example. We got 3 premises and a conclusion, and what do we do? Well, the conclusion looks pretty tough to get. I mean, if this was just a conjunction and it didn't have the negation out there, you know, that might be a lot easier, but it's the negation of a conjunction. So what are we going to do? Well, there are some new tips that the equivalence rules open up. There's new tips for doing proofs. One of them, tip 6, is think about what is equivalent to your conclusion and your premises. So that'll often open up some avenues. Because we have equivalence rules, we can easily just plug in things that are equivalent. So what is equivalent to our conclusion? Well, with our new rule, do you see it? DeMorgan's. DeMorgan's, so if we, what would be equivalent to this? Well, by DeMorgan's, this would be equivalent, right? These two amount to the same thing. So if we could get this, we can then just apply DeMorgan's to it to get our conclusion we're trying to get. So that might be easier to get. Because remember, if we're trying to get a disjunction, there's a couple ways we could get that, right? If we just get one side, we could just use the rule of addition to just add the other side. So that might be really helpful. We could also get it, of course, by constructive dilemma. That's another way to end up with a disjunction like that. So let's see what we got with our premises. Well, if you think about that second way I mentioned to get a disjunction, notice that we have 2 conditionals already that end in what we need over there. Not A and not B, right? So these are great ingredients, but we would need to, if we were going to use constructive dilemma, we need a disjunction, an either or with not G on one side and not H on the other. Well, if you look at line 3, what's equivalent to line 3? Well, by DeMorgan's, just like we did with the conclusion, that's actually exactly what we need. So equivalent to line 3 would be what? Not G or not H by DeMorgan's. So that's 3 DeMorgan's. And then we already saw that constructive dilemma could give us this statement in blue up there. Using these conditionals, if we just had this disjunction, which now we do. So what? 1, 2, and 4, constructive dilemma, right? We have this either or, and if not G, then not A. If not H, then not B, right? And it's going to be a disjunction, right? If either this or that, then either this or that, right? And now all we got to do is use equivalence rule DeMorgan's on 5. So that's 5 DeMorgan's, and we're going to get our conclusion. And of course, this is just going from the right side of DeMorgan's to the left. So we pull that negation out and then flip from an either or to an and. That's 5 DeMorgan's. Awesome. So remember that rule. It can be very helpful, or not rule, but the tip. Think about what things are equivalent to your conclusion and your premises, and you can just jot them over to the side to see if getting that statement that's equivalent would be easier or helpful. And so that's a helpful little tip when you're trying to figure out what method to use to end up with your conclusion. Another tip that our new equivalence rules open up for us is that improves instances of conjunction or addition can then lead to useful applications of DeMorgan's. And this is one of those combos, the idea that you want to use, say, conjunction and DeMorgan's together, or use addition and DeMorgan's. So here's some examples, very simple examples where this works. So say you need to get this, the negation of a disjunction, and of course you're going to soon recognize this is prime use for DeMorgan's when you have the negation of a disjunction. Well, if you could just combine conjunction with DeMorgan's, you're going to get what you need. So using the previous tip 6, we know our conclusion is equivalent to this, right? By DeMorgan's, not E and not F. So you can just do a combo, right? You combine, use conjunction with 1 and 2, not E and not F, 1 and 2 conjunction, and then you take what you got and apply DeMorgan's, and you just get exactly what you need. So this is a nice combo to remember that you should at least, be mindful of. Another one is where you use addition with DeMorgan's. So here, tip 6 tells you, well, what's this equivalent to? Our conclusion is equivalent to this. And we know for a disjunction, if we can just get one side, we can add the other. So our combo will take not G and just add what we need, and not H. That's step 1. And then the next part of our combo just applies DeMorgan. So that is that. So 2 DeMorgan's. Awesome. To see more examples of how to use our new rules in proofs, make sure to check out the proof practice videos. I made separate videos where I go through proofs in 8.2, and I just talked through my thinking and strategy as I'm doing them for you, and I've broken them up into individual videos. So make sure to check that out, because this is definitely something you need to practice to get good at. In section 8.3, we're introduced to 5 more equivalence rules, bringing our total to 10. So the first equivalence rule in 8.3 is distribution. Distribution, the idea here is we're taking something, a statement, and distributing it across something else in parentheses. Of course, we can reverse that, going from right to left, but there's 2 versions of this, and you'll see one version, you have a conjunction, an and one side of it is an either or. All right, so when you have that mix of and with an or within one side, then you can do distribution to it. So notice this is what you can't do, association, right? Association needs these to be the same, both ands or both ors, but when you have a mismatch, you can actually do distribution. So when you have this, you distribute the P to the S as well as the R, and what you're going to get is P and S or P and R. Now, notice now in the result, you just have one S, you just have one R, but now you have 2 P's going on. All right, so notice that. Also notice, in order to remember what goes where with the ands and the ors, if for distribution, if the main operator is an and you use the rule on the statement, the result is going to be the other sign. So if you start with an and as the main operator, the resulting statement, the main operator is going to be an or. So keep that in mind when you're trying to figure out, should this be an and or an or, and then should this be and with ors on each side, or how it is there. Keep that in mind, that the main operator switches to the other sign. And just like some other rules, we have 2 versions. You can also have where you have an either or, and one part of the either or is a conjunction, right? We distribute that, and the result is going to be this bigger conjunction that resulted from a disjunction. This rule is going to open up some new things with proofs. So we get a new strategy with this rule. And with this, we're going to combine distribution with simplification. So let's take this example and see what to do here. We're trying to get D as our conclusion, and these are premises. So we see D in line 2. So you probably recognize it'd be nice to get the left side of this conditional in 2, and we can do modus ponens to get our D. That'd be great. But how are we going to get F or L? Well, of course, if we just got one side, we just got F, we could get L by adding. We could do constructive dilemma. What else? Well, what would be the result? So as you grow familiar with the rules, you'll start to recognize more and more that this is prime. You could use distribution on line 1. You recognize the or, and one side of it's an and. So what would one look like if we applied distribution to it? Well, it's going to be F or G, and then we'll put that in parentheses, and because now the main operator needs to switch, and F or L, right? So that's line 1 distribution. That's equivalent. And that is perfect because now we get this F or L as part of a conjunction. And we can, of course, just pull this out so we can use it. We'll pull out the F or L to make it all by itself. And that's 3 simplification. So now we have what we need. We can use line 4 with line 2. And that's going to be modus ponens 2 and 4. And that'll give us D. So remember that tip that you can use that combo of distribution, especially if the result is this big conjunction, because then you could just simplify the big conjunction to pull out one side or the other, if that helps you in your proof. Can you tell whether these are correct or incorrect applications of distribution? So the first example, what do you think? Is that correct? Well, what is your answer? The answer is yes, this is correct use of distribution. We have, this is of course going from the right to the left, and the thing that got distributed, we're reverse distributing that C, pulling it out, and then inside of the parentheses, now we have the not L, we have the S, and what about the signs? Well, our main operator here was the or, and now it switched, the main operator is an and, right? And then the other one switched as well. These switched from ands to an or. So that works. What about this one? Well, this is going from left to right, if anything. So we'd have the K and the X, and then over here we have the K and the R. However, we have an OR as the main operator here, and we have an OR as the main operator there. So no, this is not correct. That's not distribution. This would not be equivalent to line 1. Another new equivalence rule we have, exportation. This one is not going to be used too often, most likely, but it's got very specific cases where it helps. So if you see this combination, you have an if-then statement, and the if part is an and. So P and if P and S, then R. That's going to be equivalent to if P, then if S, then R. Right, and this makes sense, right? So here is an English example. So say you have, if Sue is intelligent and she studies hard, Sue is intelligent and she studies hard, then she gets good grades, right? If both those things, then she gets good grades. Well, that's equivalent to this. If Sue is intelligent, then if she studies hard, she gets good grades, right? And those two English statements, they're equivalent, right? Whenever one's true, the other's true. Whenever one's false, the other's false. Awesome. So, and notice here, right, the main operator is the second operator. And over here, the main operator is the first operator. And where is, in the one where you have an and, where is that and? It's in the if part, the antecedent. If you have an and in the consequent part, that's not going to work for exportation. It won't result in something equivalent when you try to do something like that with it. So notice that. So let's see. Let's try this example proof, and we'll see where exportation could be helpful. So if you practice and are familiar with the rules, you'll probably recognize, oh look, this is an if-then, and the if part is an and. So that's something that I could use exportation on, and that might be helpful. But how would we come to a decision on what to do? We're trying to get a conditional, if D, then J, and D is all tied up in line 1, this complicated thing, not J. What are we going to do to get that? I mean, this is basically saying if both of these things, then not J. And this is just saying, well, you know what? If just one of those things, if D, then not J. So how would we get that? This is basically just saying, hey, look, yes, we have this side. So if we have this side of the and, then all we need is that side. So if we let's apply exportation to line 1. What we get, instead of P, like in the rule, we have not W, right? And that's fine. We're not replacing it with just W, we're replacing it with not W. So not W, and then we'll have an arrow, and we're going to get what? Now a new conditional within the consequent, right? So if S then R, this is going to be if D then not J. So that's one exportation. And now it's perfectly set up for 2 and 3 together for modus ponens, right? 2 and 3 modus ponens. And that's just going to give us this. So if D, then not J, right? Awesome. Take a look at this example. This is an inference from line 1 to line 2. Is this an instance of correct application of exportation? What do you think? Well, we have a conditional, and the consequent is a conditional itself. So that is like the right side of exportation. And then down here in line 2, now we've put not M and N as the antecedent. So yes, even with those negations in there, that's consistent. So that's a correct use of exportation. Awesome. Redundancy is a rule that is super obvious why it's true. The idea is, so you have some statement. Well, guess what? You can replace it with that same statement or that same statement, right? So if the pizza has cheese on it, then we can conclude either the pizza has cheese on it or the pizza has cheese on it, right? Obviously. And you can do the same thing with and. You can also drop one, right? Either this, where this is the same thing. You can just drop it to one statement. It's obvious why that works, right? But it's helpful to have this rule in some cases in a proof. So let's look at this. We have 3 premises. We're trying to get B. What do you notice? See any pattern of a rule? Well, hopefully you see that this is great for constructive dilemma. We have a either or, and then we have conditionals going from each side. This goes from the left side, this goes from the right side to something new. So what will result if we apply constructive dilemma? 1, 2, 3, constructive dilemma. The result is going to be B or B. And we're trying to just get B, and it's going to be very hard to get it from these lines because all of these, it has the B trapped in a conditional. How are we just going to get B by itself? Well, redundancy is super helpful here because we can do that constructive dilemma to get an either or and then just write B. Intuitively, that's obvious, but we need an official rule to make that work. So that's redundancy. Awesome. Can you tell whether these are correct uses of redundancy? What about this one? Is this correct? Looks like we took the not be or not be part of this bigger biconditional and we applied redundancy. Yes, so that's correct. Always remember you can use equivalence rules, apply them to part of a larger statement. What about the next example? Is that redundancy? Yes, that is correct as well. Here we took something more complex than what we had before, right? Instead of something like not be being the thing that is redundant, here it's actually y or p, right? We took y and p and replaced it with y or p and y or p. That's a valid use of, or I shouldn't say valid, that is a correct use of redundancy. So awesome. Our next to last equivalence rule is material equivalence. This rule is the one and only rule we have that directly works on biconditionals, right? We have a lot of rules that, of course, they can result in a biconditional if the biconditional is a part of some larger statement, but this is the only rule that directly applies to biconditionals. So there's two versions. You can go from a biconditional to two different things. One, think about the truth table for a biconditional. A biconditional is true when both sides have the same truth value. If they have different truth values, recall, then the biconditional is false. So if this is true, then we know that either both P and S are true or both P and S are false, right? And that's what this first version represents, right? So both P and S are true or both P and S are false. So that's why we have the first version. The second version gets at intuitively what a biconditional is, right? It's just two conditionals basically going in both directions. So that's what this is. Instead of an or, this is an and. It's saying both from P to S and from S to P. That's pretty straightforward. And don't forget, you can go from the right side to a biconditional. In fact, if you need to prove a biconditional and you don't have a biconditional anywhere in your premises that you're starting with, this is probably one of the best ways to get it in a lot of cases. First, you prove a conditional going one way, then you prove a conditional going the other way, and then you can just use conjunction to put them together and use material equivalence then to get your biconditional that you need. So here's an example. Is this an instance of material equivalence? Yes. It's going from a biconditional and it's doing the second version. Now, of course, instead of P, like in the rule, we have something more complex, S or T, and that's fine. So what about this one? This one's going from, looks like the right to the left, and it's using the first version, the disjunction. And yes, this is a correct application, material equivalence. And our very final rule is material implication. Right? Instead of ME for material equivalence, now we have material implication. And this is saying that these two things are equivalent. A conditional, or you can have a disjunction where you negate the if part, right? And now this might seem odd, right? If P then S, equivalent to not P or S. Well, take a look at a truth table for these two statements. We'll fill it in like our standard method of filling it in. And notice that every time one of them is true, the other comes out true. Every time one of them is false, the other one comes out false. So they are equivalent. No matter what the situation is, they're always going to have the same truth value. So whenever you see one, a conditional, you can replace it with a disjunction where you negate the if part. Or if you have a disjunction and there's a negation on the left side, then you can replace it with the conditional without that negation on the if. This is actually a very helpful rule. You often will end up using it probably a whole lot on proofs. Let's try this proof where material implication is going to come in handy. So, man, we have this premise and conclusion. That's all we got. We're trying to get this disjunction, either or, and we're working with a conditional. So what are we going to do? Well, we don't have a whole lot of rules to get to a disjunction from a conditional, except material implication. It's actually a nice bridge rule to go from things with conditionals to things with like ands and ors. So let's see what we get. We got a if then, let's just convert it to a disjunction with material implication. So what's that gonna look like? Well, instead of L, we'll have not L, and then instead of an arrow, we have a V for either or. And then our consequent is the complicated O and G. So that's what we get when we apply material implication to 1. And now we still need to get that not L or G. Now we have not L or O and G. And you might be thinking, well, gee, why can't we just use simplification, right? Instead of, we need a G here instead of O and G. But we cannot do that because simplification is an implication rule, not an equivalence rule. O and G is not logically equivalent to G. You can't just drop half of an and when it comes inside something else. It's not going to be logically equivalent. So what can we do? Well, what happens, let's see. One of the earlier tips, of course, is see if you see any patterns or things you can do where you can apply rules to things to break things up, something. Well, if you see an or, and then inside the or, on one side is an and, hopefully you should recognize that you could do distribution. And what's that going to get us? Well, it's going to get us a big conjunction, right? Instead of the main operator being or, it's going to be an and, so a big conjunction, and both sides will be disjunctions. If we have a big conjunction and we can, of course, then use simplification to pull apart one side. So let's see what we get with distribution. So distribution on 2 is going to be not L or O and not L or G. Awesome. And it turns out, look, that the right side is what we're trying to get. And it's part of this bigger conjunction, so we can just use simplification now on 3 and pull out the right side. So that's 3 simplification. Cool. This proof actually suggests a strategy, a tip. This, I think, is what number? Tip, is it tip 8? It's one of the new tips, and that what is the tip? It's that material implication can often lead to useful instances of distribution. Is that what the tip is? Yes, I got it right. So that's something you want to keep in mind. And of course, you can look through your list of tips if you get stuck and see that. That might be a combo that helps you. Let's try this proof. We have a biconditional as a premise, and we are trying to get a conclusion where that same biconditional is the consequent of a regular conditional, right? So how do you get that? We're trying to prove that if S, then M if and only if E. We're trying to prove that from M if and only if E. Well, go back to your previous tip. What are things that are equivalent? You could write things that are equivalent to this biconditional. You could write things that are equivalent to your conclusion. You probably don't want to write things that are equivalent to your biconditional at this point, because you know in your conclusion you have the biconditional. So you don't really need to probably break that up. But what's equivalent to our conclusion? Well, our new rule, material implication, instead of this conditional, we could have this disjunction, right? Now we have either or with a negation of S. And then this part's the same. Is there a way we could get this more easily than the conditional? Yes, we can easily get a disjunction if we already have one side, right? We have that nice rule, addition. We can just add the other part. So perfect, let's do that. We just add the not S part, and we use what we have in our premise. So that's one addition. And now we can just take 2 and use material implication. And now we'll get if S, then M if and only if E. Awesome. This example actually suggests another tip for doing proofs. And that's that addition can often set up material implication. If you need to get a conditional, you already have, say, the consequent of it. Well, if you use this kind of combination, you can easily get that conditional. Likewise, if instead of this, if we had, say, just not S as a premise, something like this combination could work as well. If we just had not S, right, instead of the right side, if we had the left side, not S, so the negation of the antecedent, then we could just add the right side and then get our conditional conclusion by using material implication that way. So be aware of that strategy as well. That's it for this video, and that's also it for the main teaching videos for the rest of the course. There are, of course, the proof practice videos, which probably essential for almost everybody. If you don't practice the proofs, it's going to be hard to do well on the final exam, because the final exam is going to be mostly all proofs or small sort of snippets, like here is the application of a rule or purported, is this correct application of a rule or not? Everything related to doing proofs and correctly doing proofs. So make sure to check out the proof practice videos so you can hopefully get a little help in practice. Of course, if you have any questions about anything, send me a message. if you're doing proofs and you get stuck, and the tips aren't suggesting anything to you, feel free to send me a picture of what you have, and I'm happy to suggest things, as well as double check your work to see if you did things correctly or incorrectly. So send me that. I want to say thanks so much for being an awesome class. I know this semester has been like nothing else before in terms of probably your semesters, switching to online in the middle. So thanks for your patience as I learn how to do the online stuff and make videos. This has definitely been a big learning experience for me. I'm sorry for things taking longer, but hopefully everything's worked out. So thanks so much, and I'll see you in the practice videos.